Hello, Math 213, 221. And this is going to be our last video lecture of new material for the last test 4 here. And we're going to talk about the fundamental theorem of calculus, and we're also going to do some substitution with this as well. So let's begin. And I want to start with the summation, the limit on a summation again. So again, our summation here was all the rectangles are adding together, and then the limit is what makes that go to infinity. And then once we had that expression, we then made some notation changes, and we ultimately get our integral expression. Now, when we do the summation from 1 to n, that means the entire area that we're integrating, which is from a to b. So this summation does technically equate to the definite integral, and the definite integral will always have these endpoints, and the definite integral will then give us the actual area under the curve. So what we've been doing to this point without the integration limits, without the AB, is we've been getting the indefinite integral. So we're just getting the function answer, but we haven't been actually getting a number for our answer. And so that's what we're going to do today. And so the fundamental theorem of calculus has been found that this integral expression then is actually equal to, so these capital F's are the antiderivative. So that's what you've been practicing to get, the antiderivative, this capital F. So once you integrate and then you have your antiderivative, you simply plug in the endpoints and subtract. You have f of b minus f of a. And this is the fundamental theorem of calculus then, that this definite integral equals simply subtracting the antiderivatives with b and a plugged in. And we'll do some examples of that. And there are two more properties of not used too much, but although can be important at times, is we have this property from going from two endpoints, let's say a to c. You can actually break that into two integrals, one that goes from a to b and then b to c. So you can take an area and split it into two areas and add them together. And you can actually do this as many times as you want. You could split a to c into maybe 3 or 4 integrals, however many you want. And we'll have 1 or 2 examples today using that property. No examples today will actually use this property, but this simply means that if we're going to integrate from a to b, that this equals the negative of going from, I said a to b, and then we're going to go b to a. So this means basically integrating towards the left. So if we're going towards the left, then dx, remember that's the spacing of our rectangles, moving to the left, that'll actually be negative, which is what overall makes this integral negative here. But that's a relationship. If you want to simply switch the integration constants, the limits here, then that gives you a minus sign on the integral. So let's check out then some straightforward problems of the fundamental theorem of calculus, and then we're going to get into some examples that also use substitution. Let's try integral here. We're going to do from minus 1 to 1, and that's going to look like this on the right. So here's our parabola, and we're going to integrate from minus 1 to 1, and so then this green area is what we're figuring out. So we'll first recognize the integral distributes so that we can do each of these terms individually. Now it depends on how much you want to write out yourself. Usually not too many people write out this first step, but it's definitely something that you can do. So the integral distributes. So let's take our integral here, see if we can do any cleanup steps. So like this second integral, there's a constant 2, so we can pull that outside. And the third integral does have a constant 3 that we could pull outside. And then we will get those antiderivatives. So the antiderivative of x squared, remember we're going to be adding 1 this time to the exponent. So we'll get 1/3 x cubed. And we got our minus 2, the integral of x. We're going to add 1 to the exponent. So the 1 goes to 2, so that becomes x squared. And of course, we're always dividing by that new exponent there. And then the third integral, that antiderivative, we're just integrating 1. So we're going to have 3, and then the antiderivative there is x. Now before, with the indefinite integrals, we always added a plus c because it was indefinite. We didn't know what the exact answer was. But now that we do have these limits that we're going from -1 to 1, there is some new notation that comes in here. And it's usually this bar notation, although some people do use a type of bracketed parentheses here. But I find it's pretty common that people use a bar. And what this signifies here is that you have your function. Remember, this is your antiderivative. So this is kind of like the bar is like a step. It's saying, okay, we've done the antiderivative, but we haven't done these limits yet of 1 and -1. And so we usually stick these limits then on this bar. So again, what's this notation? It indicates here's our antiderivative, and then the bar indicates we haven't done the fundamental theorem of calculus yet. So remember, the fundamental theorem means once we have our antiderivative, we plug in b and then subtract off, plugging in a. That's our fundamental theorem of calculus, and that's what this bar is representing here, that we still haven't done that. So I'm going to stick a bar on all these antiderivatives here. 2 times a half right here, so that's 1. And on our bar, we are going from -1 to 1. And then our 3x is also going from -1 to 1. A little unfortunate the program doesn't keep all those bars the same height, but there you go. So this is our answers so far. We did the antiderivative, and that's what you did in the last homework. And now we have this new notation, this bar, and again, the bar indicates the fundamental theorem of calculus. Let me take this line again. I'll just get this out of the way. So let's do that. Now there's something else here that's true, is that if the bars are all the same, in this case they are all the same, and what I mean by all the same is they all go from -1 to 1. And when that's the case, we can just use 1 bar then to represent all of that. And it does save us a little bit of work by doing that. And so we'll just put 1 bar then for the entire expression. Again, you can only do that if all the bars are the same. In other words, they're all going from the same A to B. So now this is where we do the fundamental theorem of calculus. So again, it says plug b into the antiderivative. So everything in the parentheses here, this is the antiderivative, and b is 1. So we're going to plug 1 into our function here. So let's plug 1 into the function. So 1 cubed is 1. 1 squared is 1. And 3 times 1 is 1. So there we go. We plugged b into the antiderivative. And now we're going to subtract, plugging in a. We're going to take the function again, our antiderivative, and now we're going to plug in minus 1. So minus 1 cubed is minus 1. Minus 1 squared is 1. And 3 times a minus 1 would get us a minus 3. And so here's the statement we now have after doing the fundamental theorem of calculus. And then the last thing to do would just be to do a little arithmetic there and clean it up. And it is important to use parentheses here because this minus sign that's in the fundamental theorem of calculus will distribute if you have multiple terms there. So always safe to use parentheses. So what do we have here? Well, we've got 1/3 minus 1 plus 3. And then we're going to have the negative of all that. So we'll have minus a negative 1/3 to get us a positive. Negative times a negative gets us a positive 1. And negative times a negative gets us a positive 3. So if we just put that all into a common denominator of 3, so we would have 1 minus 3 plus 9 plus 1 plus 3 plus 9. So of course, just multiplying these by 3 here to get a common denominator. And then what do we have? So we have minus 3 and plus 3, so those will subtract out. And then we have 9 plus 1 is 10, and 9 plus 1 is 10 to get us 20. So let's try another one. And we'll do another one here that doesn't require any substitution yet. So here's what that graph looks like. And we're interested in the area that is from minus 2 to 2. That's the green area then, from minus 2 to 2. We're trying to figure out that area. So something that you might want to do first is pull out the constant. And then here's the integral that we need to find the antiderivative for. Now something else you might want to do is put this into the power series so we can bring this parentheses to the 4th power. We can move that into the numerator if we make the power negative. So just a property of exponents there. And now you hopefully see it's in the power function form here. So we will get that antiderivative. remember we add 1 to the exponent. So minus 4 adding 1, that'll go to minus 3. And then remember, we always have to divide then by that new exponent. So this is our antiderivative. And now we're going to stick the bar on this to indicate we have not done the fundamental theorem of calculus yet on it. And we can clean that up a little bit actually, because 3 times minus a third is just going to be a minus 1. And so here is our antiderivative. And this is what the last homework was all about, getting antiderivatives. And so what's new today is the fundamental theorem of calculus and this bar notation. So now that we have the antiderivative, we're going to plug in b. So b is the top limit. So that's 2. We're going to take our antiderivative and plug 2 in it. And so 2 plus 3 is 5. And then we're going to subtract off a. So always remember it's f of b minus f of a. So now we're going to subtract off putting a into our antiderivative. We're going to subtract off a. We're going to subtract off having a in our antiderivative. And a is minus 2. And then 3 minus 2 is 1. So here we've done then the fundamental theorem of calculus. And then the last thing would be to finish up the arithmetic on that. So 5 to the minus 3 means 1 over 5 cubed is 1/25. Then we're going to have minus a minus, that's just plus. And then 1 to any power is still 1. And then we'll get a common denominator there of 125. And so we would have minus 1 plus 125 to get us then 124. And that's our final answer. 124 over 125. That is the area of this green on the graph here. Just short of 1. So let's try another one. And let's see what this one looks like. So here's the function, and we want to find the area from 1 to the square root of 2. So the square root of 2 is about 1.4. So we're looking for this green area right there, trying to figure that out. So first off, for something like this, we do want to try to simplify things as much as we can, and at least for integrating wise, try to get things in a simpler form for integrating. And here's something where we can decompose this into fractions, something I talked about last time. And remember that means we're going to take the denominator here, s squared, and divide everything in the numerator by it. We're going to take everything in the numerator here, divided by x squared, or s squared. So s squared divided by s squared is 1. and then the square root of s divided by s squared. And we do have those two s's there that we can further combine. Remember, square root of s, remember that means s to the power half. And so combining these together, remember we subtract when we have a denominator, so we have a half minus 2. So that's 1 half minus 4 over 2 to get us minus 3 over 2. So now that we have the integral in a simpler form for integrating, now that we can distribute the integral. So it'll distribute to the 1, and it'll distribute to the s to the minus 3 halves. And again, what that simply means is we can integrate it term by term. So the integral of 1 is just s. Here's our plus sign, and we'll go on to the next term. So the integral of s to the minus 3 halves. So remember, we add, when integrating, we add 1 to the exponent. So in that case, that means 2 over 2. So if we add 2 over 2, we'll have minus a half. And then remember, we always have to divide by that new exponent there. So division by a half, we can take the reciprocal there to mean then a minus 2. And so here is our antiderivative. And this is, again, what the last homework was having you practice. And now that we have the antiderivative, we're going to indicate, using our bar here, that we have not done the fundamental theorem of calculus yet. We'll take our bar and stick on the integration limits there. So the next step is to then do the fundamental theorem of calculus. So that means f of b minus f of a. So we're going to take b, plug it into the antiderivative. So we're going to plug b into the antiderivative. And I'm just going to use parentheses to make that clear. This is f of b. We plugged b into the antiderivative. And we subtract off f of a. We subtract off plugging a into the antiderivative. So we got a is 1. We'll plug that in. And now that we've done that, we can just do some arithmetic and clean this up, at least the best we can here. So this one won't clean up too nicely here, but this square root of 2, remember that means 2 to the power half. And then a half, and that's actually times this one to get us a minus 4th. I know that might be a little goofy in seeing that here with this equation editor there. So just looking down over here, we have square root of 2 to minus a half. So remember, when you have a power raised to a power, you multiply. So you have a half times minus a half, how we got that minus 4th there. Over here, 1 to a minus half is just 1. And 1 minus 2 is minus 1. And then minus gives us a positive 1. That part's not too bad. And then finally, 2 to the minus fourth, we can put in the denominator. And then we're going to have combining these two together. So 2 to the power 1, that means 4 over 4 minus 1/4. They get us 2 to the 3/4. And that is our final exact answer. So in my math lab, they may want the exact answer or they may want a decimal answer. So you just plug that into your calculator and carry it out to 2 or 3 decimal places, whatever it's asking for. So let's check out another one. And I wanted to do the absolute value sign here for 2 reasons. One is that you should learn how to deal with the absolute value sign, as well as this one also allows us to do one of the other integral properties. So first off, how do you deal with the absolute value sign? And remember, the absolute value sign you can always break down into 2 equations. So we can say the absolute value of x equals x when we know x is positive. Whoops. So the absolute value of x, we can say simply equals x when we're dealing with 0 and positive numbers. And then we can say the absolute value equals minus x when x is less than 0. And so we can always break the absolute value into these 2 equations. So because we can break the absolute value sign into these 2 equations, means then our integral is also going to break into 2 pieces. And what are those pieces going to be? Well, when x is less than 0 will be one piece, and when x is 0 and greater will be the other piece. So we're going to use this property then, that we can take our integral and break it into pieces. So we're going to go from minus 4 to 0. So this is when x is less than 0. In this case, the absolute value is minus x. And then we'll add to that our next piece. So our next piece now is going to go from 0 to 4, which completes then our entire trip from minus 4 to 4. And 0 to 4, this is when x is going to be positive, and when x is positive, we can replace the absolute value sign just by x. And this minus sign means minus 1, that's a constant, so we can pull that outside the integral. And so there's our expression. And this again results from breaking the absolute value down into 2 equations, so we can get rid of the absolute value sign. And then breaking that down into 2 equations then means we're breaking our integral into 2 parts. And so now we can do these integrals. So we're going to have the integral of minus x. So we're going to add 1 to the exponent. So we'll get a 2 there. And again, remember, we have to always divide by that new exponent. Plus, another integral of x. That's another 1/2 x squared. So these are the antiderivatives for the individual integrals. But notice this time that the integration limits are different. And so we can't combine these into one integration bar. We're going to have to use two. So this first antiderivative is going from -4 to 0. And the second antiderivative is going from 0 to 4. So again, just try to be clear here. We got our antiderivative, and then the bar indicates we have not done fundamental theorem of calculus yet. So we're trying to break this into our steps. This first step being setting up the integral. The second step being getting the antiderivative. And then the third step being doing the fundamental theorem of calculus then. So we're going to do f of b minus f of a. So we're going to take the first antiderivative and plug in b, which is 0. So plugging 0 into all of that will get us a 0. And then we subtract off plugging in a. So now we're going to take our antiderivative and plug a into it, which is -4. So we'll have -4 squared to get us then a 16. 1/2 times 16 then will give us an 8. And then minus and minus will make this a +8. And this is what we got for the fundamental theorem of calculus on the first antiderivative. And now we'll go to the second antiderivative. And now we're going to plug 4 into that. So 4 squared will give us 16. And then 1/2 times 16 will give us an 8. And then we're going to add to that. I meant subtract there. Again, the fundamental theorem of calculus is f of b minus f of a. Over here, we ended up getting a plus sign because of two minus signs. So we do f of b minus f of a. So we plug a into our function. And a, in this case, is 0. So this whole thing will be 0. And this is our answer from the fundamental theorem of calculus. And so all of that equals 16. Now 16, hopefully, is something, if you think about it, you can get from geometry over here by looking at the absolute value function. So if you put these two green areas together, that forms a perfect rectangle. That would be a 4 by 4 rectangle. So 4 times 4 gets us 16. So let's try another one. And pi and e tend to mess with people's brains sometimes. I think that's because people tend to see pi as a symbol, which it is, but remember, it's also connected to a number. So I think people confuse pi and e sometimes to be a variable when you need to connect pi and e as being a number. So this represents a number raised to an exponent, which is then an exponential function. So here's our exponential function on the right of what pi to a power looks like. And we want to integrate from -1 to 0. And so there's our green area there that we're looking for. So we are integrating an exponential. Remember, an exponential is itself taking the integral or the derivative. It's always itself. Also, but remember, if we would take the derivative of this, so the derivative of an exponential is itself, but then there's a natural log of the base that pops out when you take the derivative. When you integrate, though, that natural log will pop out then in the denominator. So there is our antiderivative. That's our first step we're doing. And then we stick the bar on that to indicate, okay, we've found the antiderivative. There it is. But we haven't done the fundamental theorem of calculus on it yet. So there's our first step. So now we'll do the second step, which is the fundamental theorem of calculus. So we're going to take our antiderivative and plug 0 into it. So plugging 0 in here means we just have pi to the minus 1. And then we subtract off plugging in the lower limit. So the lower limit here is minus 1, so we'll plug in minus 1 for x. So minus 1 and minus 1 will get us a minus 2. And that is our answer. Of course, we always want to try to do our best to clean it up as much as we can. And we do have a 1 over natural log in each term, so we can factor that out. And each term also has a pi. So this has a 1 over pi, and this has a 1 over pi squared. So each term has at least a 1 over pi. And then that would leave us then with 1 minus 1 over pi. And maybe clean this up slightly more by sticking the pi there, and I get rid of that whole parentheses. And that's about as cleaned up as that's going to look. So there's our final exact answer for this green area here. My math lab is almost certainly not going to want this as an answer, though. They tend to prefer a decimal number. So you will have to use your calculator here and give your answer to whatever decimal places. There are usually 2 or 3 they want. So for our next examples, we're going to do some substitution. So last time with substitution, we didn't have any integration limits, so we didn't have the a and b on the integral bar. This time we do, and when we make a substitution, chances are that we'll also change the integration limits, the 0 and the 1 here. So let's see how that works out. So let me just pull up on the right what this new function is. So there's the function, and the green area is the area we're trying to figure out. So looking at this, we have 2 polynomials, t cubed and 1 plus t to the 4th. And so we'll choose the polynomial that's largest. It has the highest degree. That's the 1 plus t to the 4th. And once we have our u substitution, remember we're always going to take the derivative of that. We want to take the derivative of both sides with respect to x. Well, actually, we're using t here. Derivative of a constant is 0, and the derivative of t to the 4th is 4t cubed. And remember, with the derivative, we then use that to solve for dt. And then we'll divide both sides by the 4t cubed. And we have our expression for dt. And so recall from last time then that we just plugged that stuff into the integral. So 1 plus t to the fourth is u. And so that all there is just u cubed. And then dt is du over 4t cubed. And those t cubes cancel. And the 1/4 we can pull outside the integral. And here is our integral so far. So this is what we did last time, where we didn't have any integration limits. Now the integration limits originally are in terms of t, 0 and 1 are in terms of t. So we need to get these numbers now in terms of u, and we have our equation to do that. So if we plug in, say, t equals 0, the bottom limit, well, if we plug in t equals 0, then u equals 1. And so the 0 on the bottom limit, the bottom of the integration bar, becomes 1 then, because we're plugging 0 into the u equation, and we're getting then that u is 1. And we'll do the same for the 1, because this is t equals 1. So now if we plug in 1, u equals 2. And so these are our new integration limits then that are in terms of u. We always have to make sure that we're being consistent with how we're changing things. So here's our integral. And that one's simple enough, just a power function. And so remember, we always add 1 when we integrate to the exponent, so the 3 becomes a 4. And we always have to divide by that new exponent. And then 1/4 times 1/4 is 1/16. So that is our antiderivative, and I'm going to stick the bar on that to indicate we haven't done the fundamental theorem of calculus yet. And so there you go, there's our antiderivative. And then the last step to do the fundamental theorem of calculus here, remember that's f of b minus f of a. So we're going to plug b in first, that's the 2. So we're going to have 2 to the 4th, which is 16. That's f of b. And then we do minus f of a. So we take the function again. And now we're going to plug 1 into it. So 1 to the 4th is 1. And we'll clean it up a little bit. So 1/16 times 16 is 1. And then we have 1 minus 1/16. So getting a common denominator there of 16 would then mean 15/16 for our final answer. So let's try another one. And let me show you what that looks like. There's the function. We're going from -1 to 0. So again, there's our green area that the integral is going to give us. And another substitution example. And my math lab does do a pretty good job of telling you this one needs substitution. So to help you along with that, make sure you're looking for that. So again, two polynomials, x cubed, and the other one's x to the fourth plus 9. We choose when they're a difference of 1 degree, then we choose the larger one. And again, remember, this tends to work. Doesn't always work, though. And then once we have our new variable defined, we take the derivative, in this case with respect to x, and the derivative of x to the fourth is 4x cubed, and the derivative of 9 is 0. There's our derivative of u. And then remember, we take this to solve for dx then. So multiply both sides by dx. Divide both sides by 4x cubed. And now we will take our integral and plug this information in. So instead of x to the fourth plus 9, we know this is, or we're calling this u. And then dx is now going to be du over 4x cubed. And if we look here, the x cubes will cancel. And the 1/4 is a constant that we can pull outside the integral. And also recall, square root of u is u to a half. And we'd really like to get this into the numerator so we can use the integral for a power function. And so taking u to the half into the numerator changes the sign of the exponent. And there is our all prepared integral. It's all prepared to go to write in a state we want of being the integral of a power function. But of course, we're doing substitution, and I can't forget to change those limits. And this is something that can be forgotten. You saw right there. I just forgot to do that. Make sure when you're doing substitution that you're going to check these limits and change them into u. So let's look at the bottom one. It was originally -1. So we're going to plug that in for x here to get what it is when it's u. So -1 to the fourth is +1, and 1 plus 9 is 10. And so -1, when x is -1, u is 10. And when x is 0, so when x is 0, u is 9. And now the integral is ready to go. So let's get that antiderivative. So u, we're going to add 1 to the exponent. So -1/2 plus 1 would get us a +1/2. And then we always have to divide by that new exponent. And then division by 1/2 is the reciprocal, so we can take that as a 2. And then finally, 2 times 1/4 would get us 1/2. And that's our antiderivative. And now we'll stick the bar on it to indicate that we have not done the fundamental theorem of calculus. So there's our step of getting the antiderivative. And then once we have the antiderivative, we'll go ahead and do the fundamental theorem of calculus. We take the function, plug in b, which in this case is 9. So we're going to plug in a 9 here. The square root of 9, the square root of 9 is 3. And it's f of b minus f of a. So now we're going to take the function and put a into it. A in this case is 10. So we're going to have the square root of 10. And so our final answer, our exact answer, is going to then be 3 minus 1/2 times the quantity 3 minus square root of 10. And that's the best we can do clean up that final answer. Again, with MyMathLab, you will have to use your calculator most likely to get a decimal number for that. And that's our area for this green part on the graph. Now you might have noticed, maybe or maybe not, this is the first example we've had where the green area is actually below the x-axis. So every example I've given so far, the green area has always been above the x-axis. Notice this time it's below. And if we look at our final answer, the square root of 10 is a little larger than 3. So our final answer is a negative number. And this is important to remember, that the area below the x-axis, the integral will output as negative. And you can understand that because when we build our rectangles, remember this ultimately comes from the infinitely many rectangles, when we build our rectangles down, then their height becomes a negative number. And so then overall this area becomes negative. And this will be important because of what I like to call physical area, the area you would think of in physics. Because in physics, area is always a non-negative number. So in physics, you wouldn't consider this area negative. You would actually take the absolute value of this area. Since the area is negative, taking the absolute value then would give us the physical area. Now, in both your books, 213 and 221, they do make a statement about this. And in 213, they tend to call this the total area. So you'll have questions that'll say, figure out the total area. And that means you want to take these negative areas and make them positive. And for 221, they just call this the area. And I'll do some examples here. But something new moving forward, area below the x-axis, the integral will output as negative. So let's check out an example of that. So here's a new function, and here's what it looks like off to the right. And it does have a square root function. This function, that's the entire function. It just ends at minus 2 and 2. And that is because the square root can't take the square root of a negative number there. And we're going to integrate this from minus 2 to 2. So you can see that means this green area here. So we're going to have negative area on the left, because that's all below the x-axis. And we'll have positive area on the right, because that's all above the x-axis. And these are symmetric, so you should be predicting that this integral will equal 0, because the integral is going to measure an equal amount of negative area to positive area. So our prediction here is that this integral should be 0. So this is a substitution integral. Again, we have a polynomial of x and another one of 4 minus x squared. They differ by 1 degree, so the best route here would be to choose the higher degree polynomial. And once we define u, we'll take the derivative with respect to x. So the derivative of 4 is 0, and the derivative of minus x squared is minus 2x. Once we have our derivative, we solve for dx. So we'll multiply both sides by dx, divide both sides by minus 2x. And that minus sign I'm just going to stick in front there because it looks nicer. And then once we have our information, we will plug it into the integral. And I'm going to actually erase the integration limits this time so I don't forget that. And so our 4 minus x squared is what we're calling u. And then dx is now a minus du over 2x. And that minus sign is a constant, so that will pull outside the integral. The 1/2 here will also pull outside the integral. These x's will cancel. And so we're just integrating the square root of u, which is u to a half. And now we have to take care of our limits. So our limits are in terms of x. We need to get them now in terms of u. So we'll simply plug them in. So minus 2 squared is positive 4. 4 minus 4 is 0. So when x is when x is minus 2, u is 0. And when x is positive 2, 2 squared is 4. 4 minus 4 is 0. So we get 0 over 0 here for our integral, which technically means our start and stop point is at the exact same position. But just for completion, I will still work this all out since we could use a little practice here. So let's get this antiderivative. So the antiderivative of u, so we add 1 to the exponent. So 1/2 plus 1 will give us a 3/2. And then we always divide by that new exponent. And then we clean that complex fraction up. So 3/2 becomes then our 2/3 here. And then 2/3 times a half will give us 1/3. That is our antiderivative. And then to signify that we have not done the fundamental theorem of calculus, we stick the integration bar on there. Now, some of you may be asking, could we have stopped initially when we found out we were going from 0 to 0? Yes, we could have stopped there, absolutely. I just want to still go through the steps so you can get some practice in. So there is our antiderivative. And now, remember, the next step would be to do the fundamental theorem of calculus on it. So that means we take our function and then we plug in b, which of course is 0, and so that whole thing is 0. And then we'll have minus plugging in b again, which is 0. And that is our integral answer. And sometimes I like to call this the integral area. It's the area we get from integrating. So this green area you're seeing is the physical area, Because this green area, the integral just said, is a total of 0. So if we want to know, well, what is this green area then? Well, since they're symmetric, we could just integrate, say, from 0 to 2 and figure out what half of this is, and then multiply by 2. Another thing we can do is break the integral into 2 parts and make the negative side positive. And I'm going to take that approach. So let's start with the original problem again. And now this problem is symmetric, so we could just do one side and multiply by 2. That's definitely true and the easier route to go. But let me just do this assuming maybe they weren't symmetric. So maybe both sides were different. So what we would have to do then is change these limits so that we go from -2 to 0, because that'll be the negative area, and then 0 to 2. So we would use the integral property then, and we're going to go from -2 to 0, and then we're going to add to that the next area, which then was from 0 to 2. So again, it's a property of an integral that we can do. And here's where we make the change to our physical area then. Because we know, by having done the problem or looking at the picture, we can see that this first integral is going to be negative. It's going to give us this area but as a negative value. So to fix that, we'll just put a negative sign in front of it. So that may not sound too mathematical, and what the justification for that is. Remember, this just has to deal with definitions, and we define area to be positive, and so we're just going to force that minus sign into to meet our definition that area is always a positive value. So now this integral, we've already actually done the integrals here. We've already figured out through u substitution what they are. And actually, let me just copy that one down from above. So we did all this already, transferred it to u. And now we do have to fix this up, though. And we have to fix these limits. So first off, we're going from -2 to 0. That's in terms of x. So we'll go back up to our u equation. So when x is -2, u is 0. And then when x is 0, u is 4. Let me just show that again really quick here. Comparing it to where we are, so we're at this integral here in terms of x, and we're now going to change it to the u's. So our -2 to 0 becomes 0 to 4. And also recall that we are brute forcing this minus sign in here. So we're going to brute force that minus sign in right there to force that negative number to be positive so we can meet the definition of area being positive. And then we're going to have this integral again. But now we're going from 0 to 2. So let's check out what that means in terms of u. So when x is 0, u is 4. And when x is 2, u is 0. So here we go. Here is our expression, our physical area in terms of x. Here is now our physical area in terms of u. And again, we did this integral. So our first integral here, u to a half. We know that goes to u to the 3 halves. And then we always divide by that new power. And dividing by 3 halves is equivalent to 2/3. And then we have plus our next integral. Again, another u halves. And that becomes then, again, 2 to the u thirds. Now these are the antiderivatives. These are the antiderivatives. Remember, we're not done yet. Once we have the antiderivatives, we then have to indicate we haven't done fundamental theorem on them yet. So the first integral goes from 0 to 4. And the second antiderivative will go from 4 to 0. And so there we've done the antiderivative for our integrals, and then the bar indicating that we will now do the fundamental theorem. So we got our minus 1/2 sitting out in front of everything. And so fundamental theorem on this first antiderivative, that's f of b minus f of a. So we'll plug in 4. And then we subtract off that function again, but plugging in now the lower limit here, which is 0. So we'll plug 0 into there. And of course, that'll then make all of that 0. And so we can just get rid of that. And just really quick here, 4 to the 3 halves. Remember, the 1/2 means square root. So the square root of 4 is 2. And then 2 cubed is 8. And then 8 times 2/3 will get us 16/3. So that's the number for our first fundamental theorem. And now we're going to do the second one. So f of b minus f of a. So now we're going to take this and plug in 0. So if we plug 0 into that, well, that's all 0 then. And then we subtract off, plugging in the lower limit, in that case 4. We'll plug a 4 into that. And again, 4 to the 3 halves is 8. And then 8 times 2/3 is 16/3. And of course, the plus 0 we can just get rid of. And so minus 16/3, minus 16/3, we can add those two negative numbers together to get a minus 32/3. And then for our final answer, because we have a minus times a minus, so now we have a positive answer. So we have 32 divided by 2 to get us a 16/3. And 16/3 then is the physical area. That is the area you're seeing in green here. 16/3. Now remember, the integral considers this green area to be 0. Add it all up. So whatever works for you, try to make a distinction between the integral area, because that will always mean below the x-axis is negative area. Try to distinguish that from the physical area, which is always a positive number. So let's try another one. Get a log function in here. And here's what the graph of that looks like. And we're going to integrate from a half to 2. So that's the green area you're seeing over here. So you can see from minus half, or I'm sorry, positive half to 1, this is going to be negative area from the integral. And then here will be our positive area. So the integral is going to add all that up. So whatever number we get here from doing this integration is going to give us this total area integral-wise, though. So we'll have a plus area and a minus area. And let's get the integral area first. Let's just do it that way. So we do have a log function here. And remember, if you see a log function, make that u. And once you have your definition for u, take the derivative. And the derivative of log x is 1 over x. And then once we have the derivative, we'll solve for dx, because we'll need that for the substitution. And then multiplying both sides by x. And now that we have our substitutions here, we'll put them into the integral. So first off, this 2 is a constant, so we can just pull that outside. And we're going to say, we are saying that log x is u, and dx is x du. And then these x's cancel here, that we're just left with u. And then we can't forget about our integration limits. Since we've changed from x to u, these numbers most likely will also change. So, when x is a half, we'll have log of a half. Now I just want to say really quickly here, log of a half. Let me just write this out separately, actually. Log of a half, if you recall your log properties, we can write this as log 1 minus log 2. That's from log properties, and log 1 is always 0. And so log of a half is minus log 2. So log of a half is minus log 2. And now for our upper integration limit, that's 2 for x. For u, that's log 2. So we're going to integrate from minus log 2 to positive log 2. And there's our integral all set up for us. And now we'll get the antiderivative. So integrating u will get us to u squared. And then 2 times a half is 1. This is our antiderivative, u squared. And I will stick the bar on it to indicate we have not done the fundamental theorem of calculus on it. And now that we've done our second step there of getting the antiderivative, we will now do the fundamental theorem of calculus on it. So that means f of b minus f of a. So we're going to take the function, plug in the upper limit, so that's log 2. and then we subtract off the lower limit. We subtract off plugging the lower limit into the function. And just as a quick cleanup here, we do, remember from properties of exponents, we can pass along this 2 to the log and also pass this 2 along to the minus sign. So minus squared is just a positive. So minus log 2 equals positive log 2 there. And you can see that that equals 0. And that is our integral area. The integral is telling us that all this area shaded in sums to 0. So this must be equal negative area to positive area. So how then would we actually figure out this physical area? Well, since we know it's equal, we could just do half of the integral. So we could do a half to 1, and then just multiply that by 2, or we could do 1 to 2 and multiply that by 2. But I do want to take the general case if they aren't equal on how you'd go about doing that. So let's start back with our original integral. And remember, to figure out the physical area, we're going to force the negative area to be positive. So our integral, we're going to break first into these two pieces so we know which piece to force to be negative. And that's going to be from a half to 1. A half to 1 represents this negative green area, and we're going to force that to be positive by multiplying all of that by a negative sign. Now I do have to delete this equals on the left because the equal statement is no longer true once I force the minus sign in there. Because remember, we're changing to the definition of area. That area is always positive. And then we're going to have our integral again, but now we're going from 1 to 2. And we know that'll be positive, and so we don't have to do any changes there. So here's our physical area. And again, this expression no longer equals the original expression because we've changed it to meet the definition of area. And now we'll do our use substitution on this. So again, it's something we already did. This integral becomes this u substitution, so it's just the integral of u du. So actually, why don't I just copy that one? And so we're going to go from a half to 1. That's in terms of x. So we have to go back to u and see what that means. So a half means going from log half, remember log half is minus log 2, and to 1. Log 1 is 0, and so this top one then is 0. And again, this is our answer for the first integral here, and this is also the one that we force a minus sign on. And now we'll go to the second integral. And a second one is going from 0. And we're going from, in terms of x, we're going from 1 to 2. 1 to 2 for x. plugging that into the u equation, so log of 1 is our bottom 0 there, and then the 2. So we'll have log 2. And so here is our integral now in terms of u, and now we'll get those antiderivatives. And I'm going to stick the minus on there for the first one. And the integral of u is 1/2 u squared. And then that's also, of course, the next antiderivative, because both integrals have the same antiderivative here. It's only the limits that are different. So it's the same antiderivative, but it's the limit when we do fundamental theorem of calculus that's different on them. So this first one goes from minus log 2 to 0. And then the second one is going from 0 to log 2. And so there is our antiderivatives there. And now our next step will be to do then the fundamental theorem of calculus on it. Let's do the first antiderivative here. So we plug in 0 first, and plugging 0 into this will just get us a 0. And remember, it's f of b minus f of a. So now we're going to plug minus log 2 into this. And minus times a minus here will get us a positive. And of course, the 0 we can just get rid of. And again, minus log 2 squared equals log 2 squared. And this is our number for the first fundamental theorem of calculus. And I will add to that the next fundamental theorem of calculus. So it's f of b minus f of a. So now we're plugging in log 2. And then we subtract off, plugging in the lower limit. Now the lower limit in this case is 0. Plugging 0 into the antiderivative gets us a 0. And so we can just get rid of that. And so that's our number answer. We'll clean it up a little bit. And these are like terms. So a half log 2 squared plus a half log 2 squared. Half plus a half means 1. And then there is our final answer. 2 times log 2 squared. And then that is the physical area. This is the area that you're seeing in green. So again, just to be clear, the integral area we got here was 0. The physical area here is 2 log 2 squared. And so that wraps up our last lecture before the test. And the next video will be then our test review. And test 4 will be Thursday. So get prepared. And I will post all the, I can't post last semester's test since we didn't quite get through all that stuff. But I will post the test bank like I've always been posting, and you can check that out. And we will talk about test review in the next video. Talk to you then.